So now that we have the concept of the Lorentz group, let's in fact consider the particular subgroup where we've removed the parity and time reversal transformations. So let's take what is called the proper orthochronous Lorentz group, which is what is called SO plus 3, 1. So it doesn't have parity and time reversal operations. And this group is made up of combinations of boosts and rotations. Now, if you'll remember, the matrices that we used to identify what this group were these matrices lambda, which a particular example was, let's say, a boost along the x-axis, where the matrix lambda looked like this. Now, what we are really interested in is the objects that this matrix acts on. Okay, so for example, we were interested in how coordinates transform. That is, how ct, x, y, z, as seen by one observer, would be related to ct prime, x prime, y prime, z prime, as seen by another observer. And we said that if the observers S prime are related to the observers in frame S by a boost along the z-axis, or sorry, along the x-axis, that is, you think of S prime as moving along the x-axis at a speed v by c relative to the frame S, then the correct transformation to use is to put in that matrix lambda over here. So in this way, we can define this column vector. In shorthand, we can write this as a vector v. And this is a vector in a generalized sense. So this is a vector in 4 dimensions. Okay, so this is a 4-dimensional vector. And if I want to know what the corresponding vector is in the frame S prime, I would call that v prime. And so in matrix notation, v prime is a column vector, which is a 4 cross 1 column vector. And this is related to the vector v through this dot product of matrices. Okay, so this is lambda is a 4 by 4 transformation matrix, and v is again a 4 cross 1 vector. Okay, so the transformation rule for vectors is of this form. 4 vectors transform in this way. Now, this rule seems very specific. It seems like a rule in the dictionary which only works for t, x, y, and z. Because as we've seen, the transformation rules for velocities appears to be more complicated, right? We had velocities which were, let's say, ux, uy, and uz. And if we want to find the corresponding velocities in a frame S prime, okay, the transformation rule was more complicated. So what we had was something like this for ux prime. Okay, again, where observer S prime and observer S are related by a boost along the x-axis. We had ux prime is equal to ux minus v over 1 minus ux v over c square. Uy prime is equal to uy times the square root of 1 minus v square by c square by 1 minus ux v square by c square. So the rule for uy prime involves not only uy, but it also involves ux. And uz prime was uz times the square root of 1 minus v square by c square, 1 minus u ux v square square. So the dictionary for speeds appears to have, or velocities appears to have nothing to do with the dictionary that we used for space-time coordinates. Okay? So at the moment, it appears like this specification of this rule for 4 vectors is a rule that only applies to space-time coordinates. So it doesn't seem like an obvious reason why we would want to think of this as some kind of general rule. But I'll just show you in a second that secretly, the velocity transformation law has exactly the same structure as the transformation law for space-time coordinates. Okay, so let's see how this works. So what you should do is construct the following combination of 4 objects. Okay, so let's define first u square as ux square plus uy square plus uz square. And correspondingly, u prime square in the prime frame is ux prime square plus uy prime square plus uz prime square. So u is the magnitude of the speed in the s frame, u prime is the magnitude of the speed in the s prime frame. And now, supposing we construct the following quantities, that is, we construct, first quantity is 1 over the square root of 1 minus u square by c square. The second quantity is ux over the square root of 1 minus u square by c square. Then uy over the square root of 1 minus u square by c square. And uz over the square root of 1 minus u square by c square. Okay, so you construct these 4 quantities, which are defined in frame S. And you construct the corresponding quantities in frame S prime. That is, you construct the quantities 1 minus u prime square by c square, and then ux prime over the square root of 1 minus u prime square by c square, uy prime over the square root of 1 minus u prime square by c square, and uz prime over the square root of 1 minus u prime square by c square. And you ask, how are these 4 quantities in the frame S prime related to the 4 quantities in the frame S? Okay, we already know the transformation rules for ux, uy, and uz, so we should be able to figure out how these quantities are related. And if you were to work it out, what you would find is that they are related again by a linear transformation. That is, there's a 4x4 matrix, and the entries of this matrix are just what we found for lambda above in the transformation of the space-time coordinate. Okay, that is, it's this matrix over here, where this matrix is lambda that we use for the space-time coordinate. So what we see is that while ux, uy, and uz have more complicated transformation laws, the law for transformation of these 4 quantities, okay, is simple. It's as simple as the law of transformation of the space-time coordinate ct, x, y, z. Okay. In other words, if I define these 4 quantities as some kind of new quantity, which we call u, which we call a velocity 4 vector, this is related to u prime, which is a velocity 4 vector in the primed frame, as u prime is equal to lambda u. Okay, again, where this is a dot product, a matrix product. So lambda is again a 4x4 matrix, u is a 4 cross 1 matrix column vector, and u prime is a 4 cross 1 column vector. So once again, we see that the law for transformations is actually quite simple and just depends on this matrix lambda. Okay, so proving that the transformation is through this matrix lambda is a homework exercise. It's just converting the transformation of ux prime or ux, uy, and uz to a transformation of these four quantities, which I've written down as a column vector over here. And similarly, you can show that if we construct the four quantities, which are partial derivatives, that is partial ct, where I'm holding x, y, z constant, partial x with a minus sign, where I'm holding t, y, z constant, and partial y, where I'm holding t, x, z constant, and partial z, where I'm holding t, x, y constant. These four quantities are related to the corresponding quantities in the S prime frame, which is partial ct prime, where here x prime, y prime, and z prime are held constant, and minus partial x prime, where again the quantities that I'm holding constant are t prime, y prime, and z prime, and minus partial y prime, and the quantities that I'm holding constant are t prime, x prime, and z prime, and minus partial z prime, where the quantities I'm holding constant are t prime, x prime, and y prime. So you can find out this transformation law for these partial derivatives again by using the transformation law for space-time coordinates. Okay, and what you would see again is this: that the transformation rule again will be of this form: minus gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. So again, if we call this 4 vector as partial, okay, so we just in shorthand denote it as partial, where this represents a 4 vector, and this is the 4 vector partial prime, then again partial prime is related to partial through this matrix lambda. Okay, so again this is a 4 cross 1 vector, but in this case it's not a 4 cross 1 vector of numbers, but rather it's a 4 cross 1 vector of operations, that is partial derivatives. So, but again, the transformation rule for these operations is exactly the same as the transformation rule for space-time coordinates and for the velocity 4 vector that we found. Okay, they're related through this transformation matrix lambda. So what we see is that if we find the right combinations of variables, okay, that is, with velocities we need to find this particular combination over here, and with derivatives we need to take this particular combination where the first derivative with respect to time has a positive sign and the other derivatives have negative signs. And when we do that, then the quantities that we had written down, let me just denote them as x, u, and partial, x being the space-time column vector, u being the velocity 4 vector, and partial being this derivative 4 vector, which I've written down over here. These quantities all transform in the same way. Okay, so this gives us a general notion of the idea of 4 vectors Okay, that is, there are many things which transform with the same matrix lambda. Okay, so we see that in terms of the matrices lambda, the transformation rules, or our dictionary, has become much more simple. Okay, if we correctly identify four vectors, we have very simple transformation laws for these four vectors. That is, any four vector will transform in this way. Okay, the trick is to figure out what is the right combination of variables that transforms as a four vector. Okay, now apart from this, what we've seen is when we construct the space-time vector, what we've seen is that this quantity, ct square minus x square minus y square minus z square, which we call the space-time interval, is invariant. That is, it doesn't change from one reference frame to another. So in another reference frame, supposing I had this four vector, I would calculate the quantity ct square minus ct prime square minus x prime square minus y prime square minus z prime square. And what you would find is that these two quantities would be exactly the same. Now, this is obviously true, or we've checked this in the case of a Lorentz boost, but you can also check this obviously for the case of rotations. In the case of rotations, the time coordinate does not transform. Okay, so the time coordinates are the same. And x square y plus y square plus z square is a length which doesn't change under rotations. So under a general Lorentz transformation, a general proper orthogonal Lorentz transformation, this space-time interval is invariant, and we can write this rule for invariance, or we can understand this rule for invariance in a very simple way. So first, if we define this vector as x and we define this vector as x prime, what we see is that the space-time interval can be written in a very simple way. So delta s square, which is the space-time interval, is equal to x transpose, okay, dot g, where g is our space-time metric, dot x. And the statement is that this is the same as x prime transpose dot g dot x prime. Okay, and these two are obviously equal because if x prime and x are related by a Lorentz transformation, what that means is x prime is equal to lambda x, and therefore what that tells us is that this quantity is x transpose dot lambda transpose dot g dot lambda dot x, and by the property lambda of any matrix of belonging to this Lorentz group, this quantity is just g, so this is just x transpose dot g dot x. So the space-time interval is indeed invariant, and one way we can see that is by constructing the dot product of x with itself, or this, you can think of this quantity as a dot product of four vectors. Okay, so if I have any two four vectors, a and b, I would construct a dot product which we denote as a general a b. Okay, I'll use a circle over here. The circle is four vector dot product. Okay, to distinguish it from this dot, which is a matrix product. So this four vector dot product is A transpose dot, where this is matrix product. This is four vector dot product. Okay. this is a definition of what the 4-vector dot product is. It's A transpose dot G dot B. Okay, and you can easily check that this is going to be equal to, by taking the transpose of this, it's going to be equal to B transpose dot G dot A, as long as yeah, so it's just going to be B transpose dot G dot A. And now the point is that this 4-vector dot product is the same no matter which frame you calculate this in. That is, A circle B will be the same as A prime circle B prime. Okay, which is also obviously the same as B circle A and B prime circle A prime. Okay, so 4-vector dot products are Lorentz invariant quantities. That is, they are the same no matter which reference frame you calculate them in. So such quantities are also called Lorentz scalars. Okay. That is, these are quantities that do not change from one reference frame to another, just like the space-time interval is a Lorentz invariant quantity. So now you could ask, let's take some of the 4 vectors that we had constructed. So let's take, for example, the velocity 4-vector. And let's ask what happens when you construct this dot product, okay, of the velocity 4-vector. Well, you can check that in any frame, if you construct this, you will just get 1. Actually, I should be a little more precise. If I go back over here, I think I made a small mistake. So dimensionally, all things inside this 4-vector have to be the same. So what I should really do is put a factor of C here, so that the dimensions of the first quantity in this column vector agree with the dimensions of everything else in this column vector. And I should do the same thing here. So now if I define these 4 vectors in this way, so U and U prime in this way, then what I would find is that no matter which frame I calculate U circle U, I would get C square. Okay, so this would be the same as what I get in the prime frame. So indeed, this would be a Lorentz invariant quantity. This would just be the speed of light. Okay, and similarly, we can find out what we get when we calculate partial circle partial. And this we can write it out explicitly. It would be partial square partial t square 1 by c square minus partial square partial x square minus partial square partial y square minus partial square partial z square. So this is called a wave operator. Okay, because many wave equations, for example, the wave equation for light, can be written in terms of this operator. And since this operator is Lorentz invariant, this operator is going to be the same even if I calculate it in the primed frame. That is, if I calculate the quantities partial prime circle partial prime, which would be 1 by c square partial t prime square, these two quantities would be the same, okay, because they're Lorentz scalars. Okay, so these are some examples of Lorentz scalars. Okay, this operator is a Lorentz scalar, this number is a Lorentz scalar, and the space-time interval is a Lorentz scalar.